Any vector, okay? So any vector that has a length of 1 is called a unit vector. So what we need is for this to be true. Oops, wrong class. The length of the vector, we'll call it vector v, is 1. That means v would be a unit vector. Do y'all remember that notation, like the absolute value bars? Okay. So let's do an example here. Let's say we have a vector u, which is the vector 5, -7. Is that a unit vector? No. Probably not, right? I mean, it seems pretty long. If we were to try and do like a graphical representation of this, we could place it anywhere we wanted, right, on this flat sheet of paper. But if we started at the origin, we would move to the right 5 and go down 7. Right, that would be a representation of that vector. Yeah. So this is your horizontal displacement, and this is your vertical displacement. And so that would be the vector. It's obvious that that does not have a length of 1. Is it obvious? Okay. In fact, for it to be a unit vector, it would actually have to, there's the unit circle, isn't it? That vector would have to be touching that purple circle. If you started at the origin, it would have to be doing that, right? So here's my question to you. Can we find a vector? Unit vector pointed in same direction as u. So I'm actually going to zoom in on this picture a little bit more. One, two, three, four, five. 1, 2, 3, 4, 5, 6, 7. So that vector was like this, right? That was that vector. Can we find a vector that's a unit vector that points in the same direction? In other words, this one right here. Can you tell me what it is? Right? 1, -1 won't quite be the same direction, and 1, -1 won't be on the unit circle, right? 1, -1 would be outside the unit circle, and it would not point in the same direction. We can find it, though. I mean, do you all agree it exists? Yes, it does exist. So is there a way that we can determine? Well, wait a minute. Hold on. Didn't we talk about that if you have a vector and you multiply it by a number, that it either stretches it out or shrinks it or flips it over and points it in the other direction? Okay, so this vector, this purple vector, is actually just some scalar multiple of this vector. Looks like I have to shorten it, right? So I have to multiply this vector by some number that would make it have this length of 1, right? So what is that number? Well, here's what it is. I'm going to tell you exactly the formula for it. All right? To do this, we will multiply u by 1 over the magnitude of u. Huh, that's kind of weird. But think about that for a second. Let's say that this vector u was 10 units long. Okay, say the length of this vector was 10. Then this right here would have to be 1/10 of that, right? Let's say that this vector was 3 units long. Then I would need to divide this vector by 3 to make it 1 unit long. So whatever this length is, if I divide it by its own length, then it should be 1 unit long. So that's where this comes from. So this is the kind of the master idea right there, is that we need to figure out what this is and then multiply that vector by it. So let's do that work over here. So what is the length of u? There was a formula for it. It was square root of the sum of the components squared. So I just have to square these, add them together. Right, like that. That's what the length is. So this is root of 25 plus 49, which is root 74. And I'm just going to leave it like that. I'm actually not going to try and turn that into a decimal or anything. So the length of u is root 74. So to figure out a unit vector that points in the same direction as u, what I need to do is take 1 over root 74 and multiply that times this vector. Now, you may or may not recall, how do we do this sort of multiplication? This is called scalar multiplication, a number times a vector. All we have to do is almost like a distribution. You're going to distribute the number through the angle bracket. So this becomes a new vector. It'll be 5 times this, which just write it as 5 over root 74. And then comma, negative 7 over root 74. And that's it. This is the vector. This vector points in the same direction as that vector. And it should have a length of 1. How could I confirm that it's pointed in the same direction? What's one thing I could do? I could calculate the angle, couldn't I? So look, do you know how to get the angle for u? How do we get the angle of this vector? There was a formula for that. The angle of that vector is arctangent of v2 over v1, so negative 7 over 5. So if we do that on our calculator, we're going to get an angle. Can someone do that for me? Tell me what the angle is. You can give it to me in degrees. Negative 54 degrees? Okay, so this is about negative 54 degrees. About, okay? Good enough? Does that match up? Is that a negative angle? Yeah? Now, what about this one right here? If you were asked to find the angle for this one, you would do theta is arctangent of this over this, right? But do you see what would happen if you do that over that? What would happen to those root 74s? Oops. Yeah. Yeah, these root 74s would cancel out. And so you'd still be at negative 7 over 5, which is this. So you're going to get the same answer, right? So they are pointing in the same direction. I'm just verifying, that's it. We were done when I boxed this, but I'm just trying to convince you that these are pointing in the same direction. Now, can I convince you that has a length of 1? How would you determine that this has a length of 1? Have to believe? How do you find the length of a vector? This right here, right? So why don't we just double check? What would the length of this vector be? It would be, so the length of this would be the square root of this squared, right? What is that squared? If I square the top and bottom? 25 over 74 plus this squared, which would be 49 over 74. What's 25 plus 49? 74 over 74, so you get 1, so root 1 is 1, right? So the length of that vector is 1. So if somebody gives you a non-zero vector, okay, a non-zero vector, it has some directions pointed out there, and you want to find a vector that points in the same direction that has a length of 1, then what you would do is you would take the vector and scale it by 1 over its own length, and that will give you the vector you need. That does become important later on. In calculus, you do need to be able to find unit vectors pointed in the same direction as something. Not one. Not one. All right, let's just do a quick little review of the vectors, and we're going to move into the next section. So review of vector operations. So let's say you're given a vector v, which is v1, v2, and let's say another vector u, which is u1, u2. Okay, so let's say someone gives you 2 vectors. Let's talk about some of the different things that we could do. How would you do this? How would you add these 2 vectors together? These are given to you. Do y'all remember the form? This is what this form is called when they actually give you the angle brackets with numbers? The component form. So we have component forms of the vectors. If we're adding the 2 vectors together, how do you add them? Okay, so that's the visual way, right? That's the visual way. But if you just have the component forms, how do we add them? You're going to do v1 plus u1, comma, v2 plus u2. So this is actually very nice when it comes to vectors. If you have 2 vectors and you want to add them, you add their components together. So you take the x component, add those 2, that becomes your new x component. You take your y component, add those together, that becomes your new y component. Very straightforward when it comes to vector addition. How about subtraction? Same thing. Now, do we have to be careful with subtraction, though? Like in general, when you're subtracting numbers, the order matters, right? So if you do v minus u, it's going to be v1 minus u1, v2 minus u2. But if you did it the other way around, these would switch places also. All right. What are some other things we could do with these? We could take a number like c and multiply it times the vector u. How do we do? So c is a number here, right? C is a constant. If I take a constant and multiply it times the vector u, then what does that c do? We just did it a second ago. It just like distributes through. Okay, so this becomes c times the vector u1, u2, which becomes the vector c times u1, comma, c times u2. This is called scalar multiplication. So these are kind of like arithmetic, right? The arithmetic operations on vectors, adding and subtracting, scalar multiplication. Now, we already talked about last class that if someone gives you a vector, you can find its angle, right? Arctangent. We also talked about how you can find its length. Okay, so I'm not going to redo that here. I just want to make sure we understood how the vector addition and subtraction worked and how the scalar multiplication worked. Now we're going to talk about the next section, which is called dot product. And this will be all we do with vectors. We're just going to talk dot product. We're not going to do anything else. And we're going to move on to polar coordinates. All right, so dot product, 10, 5. So when it comes to vectors, we have 3 standard types of products. So when I say products, I mean when you think about product from like what you've done in your mathematical life, when you say take the product of 2 numbers, you're thinking multiplication, right? But when it comes to vectors, we actually have 3 different types of products, and I told you all about this already. The first one is scalar multiplication. Now, I just showed you what that was a second ago, didn't I? I said scalar multiplication is when you do c times a vector. C times u, which was like c times the vector u1, u2, which we said was cu1, cu2. All right, we just had that on the board, right? So that we've already covered. That scalar multiplication is nice. You just take the number and you just kind of distribute it through and you're done. The second type of multiplication is called the dot product. Okay, the dot product, you need 2 vectors. See, with scalar multiplication, you had a number times a vector, right? A number times a vector. With the dot product, you actually have 2 vectors, and we're going to try and multiply them together somehow. And that's what the dot product is. I'm going to explain how we do it, all right? We're going to do it. We're going to talk about what it means and all that stuff. But then the third type is called the cross product. And we need 2 vectors for this. Plus, we also need 3-dimensional space. And that means we are not going to do the cross product because all the vectors that we are dealing with live on a flat sheet of paper. If you start talking about vectors in 3-dimensional space, then you can start talking about this cross product. All right? So this one is kind of like off limits for now. This one we've done, and now we're talking about what the dot product is. All right, you ready to see what the dot product is? All right, here we go. The dot product just gives you a way of multiplying 2 vectors together. So let's see if you can't come up with the dot product without looking at the book or anything. If I give you 2 vectors, so here it is, dot product. Given 2 vectors, let's say v is v1, v2, and the other vector is u, which is the vector u1, u2. Then v, now how am I going to let you know I want to multiply these 2 using the dot product? Well, how about we put a dot between them? All right. Now this dot is not your standard dot. In textbooks, it's a little bit thicker and like a bolded multiplication symbol. So not to be confused with this. See, c times v, this is scalar multiplication, right? This is not a dot product. This is a dot product, but the way you can really tell it's a dot product is because it's 2 vectors. See, the only way you can put 2 vectors together through multiplication is by using the dot product. So that has to be a dot as opposed to this. Understand the difference? Now, you want to see the notation for cross product just so you can see it. That's the notation we use for the cross product, but we're not doing cross product. So if someone gives you 2 vectors, you want to dot product them, that's the notation. This would be notation for cross product, and then this is your scalar multiplication. There, okay? Remember me talking about, do you remember me talking about dog and cat coming together? No? Has it been too long? Yes? You get two dogs together, they mate, you get dog, right? Right, two dogs, dog. Two humans, German Shepherd. Yeah. Two humans, human. I mean, it pretty much has worked this way. Yes? Two cats, cat. Two birds, bird. All right. Look, right here, I tried to say this when I first introduced you to this. This is the first time we've ever seen something like this where you're taking a number and putting it together with a vector. And when you do this, what do you get? A vector. Okay? All right. So a number and a vector, cat and a dog, you get some weird dog, okay? But you get a dog. So one of these two actually comes out, right? Number, vector, you get a vector. When you do the dot product, we have vector, vector. Any guess as to what comes out? Vector? A new vector. But you think it's a vector? Vector, vector, vector? It's actually a number.
It is a number.
It's a number. Okay? Then this right here is equal to, and I'll stress in a second that it's going to be a number. What do you think the cross product gives you? A vector. Okay? It's weird. This is where things start to get weird. Okay? A number times a vector gives you a vector. A vector dotted with a vector gives you a number. A vector crossed with a vector gives you a vector. It gets weird, all right? We are not doing cross, but here's the actual answer. This is going to be V1 times U1 plus V2 times U2. It's a very clean and easy computation to do. What is that formula saying you do? Take the x component here, the x component here, and multiply them. Take the y component here, the y component here, multiply them. Add the two answers together. That's your dot product. All right? This is a number. And I would hope that at this point, you would say, what is the significance of that number? Right? Like, why have an operation called dot product that does this, that gives you a number, if it doesn't have any relevance or meaning or anything else, right? Just for fun, because we can do it? It has to have some meaning to it, right? So we will get to the meaning. Let's just do a quick example, because these dot products are the types of things you would love to see on a test. All right, so do that calculation real quick. What's U dot V? Who has it? What? It's negative 10 plus negative 3, right? So you're doing 5 times negative 2, which is negative 10, negative 3 times 1, which is negative 3, and adding the two answers together. So you get negative 13. All right. And again, the question would be like, okay, and negative 13 and, well, what does it mean, right? Just hang tight, all right? That's just the computational part of it. All right. How about this one? We're done with the example. Moving on. What would U dot U be? What if I asked you to dot a vector with itself? What would it be? Well, use that vector, this general vector right here. What would you get if I asked you to dot that with itself? You would get u1 times u1 again, right? So u1 squared plus the u2 times itself again. So u2 squared? Do y'all agree with that? Do I need to write it out? We were doing u1, u2, dotted with u1, u2. So you do this times this, that's u1 squared, plus this times this, that's u2 squared. Yes? Dot. Okay. Now this is a little harder to see, but do you realize that that's this? What's the magnitude of u? If I asked you right now, what's the magnitude of that vector u? You would do what? Square root of this squared plus this squared, right? So we had u1 squared plus u2 squared, didn't we? But there was no root there. So in order to get that root out of here, if I square both sides, the root goes away, doesn't it? So if you dot a vector with itself, it's equivalent to squaring its length. The length is a number, isn't it? If you square it, it's a number. So if you dot a vector with itself, it gives you the square of its own length. Okay. Still doesn't give us much meaning because that's dotting a vector with itself. This actually comes into play quite a bit. So this is an important property of vectors. This is obviously the definition of the dot product. That's how we define dot product. But this is a neat result that if you dot a vector with itself, it's the length of that vector squared. I have a question for you. I'll make this an example. Is the dot product commutative? Now, do you know what the word commutative means? Does the order matter? So, you know our multiplication in our number system? Our multiplication, it is commutative. 3 times 5 is 5 times 3. Does not matter the order. Subtraction is not commutative. 3 minus 5 is not 5 minus 3. But is the dot product commutative? Does u dot v equal v dot u? Question. Is that true? Should be. Because what would u dot v be? If I use the definition and I do this dotted with this, I should get u1 v1 plus u2 v2. That's what it would mean to dot these two vectors together. The question is that equal to v1 u1 plus v2 u2? Sure. Because u1 v1 is the same as v1 u1 because the multiplication is commutative. So this could flip, and they're the same thing. So the order in which you do dot product does not matter. That's good to know. Okay, another question for you. What is u dot 0? Now that's not 0, that's actually the 0 vector, right? What happens when you take a vector and dot it with a 0 vector? What is it going to spit out? 0. 0 vector or 0 number? 0 number. And the way you can see that is what you're doing is you're doing u1, u2, and you're dotting it with the 0 vector is the vector 0, 0. So when you do this times this plus this times this, you get 0 out. Okay. Let's do one more property. Is the dot product distributive? Here's what I mean. If I take U and I dot it with V plus W. So as I put that up there, I want you to look at it this way. 4 times x plus 2. You know, in algebra, we have this idea that if we have a number out here, we can distribute it. We call this distribution of multiplication over addition. We're distributing multiplication over an addition symbol. Do we have something similar like with vectors? If I dot U with the sum of two vectors, can I just dot these and then add these dotted? So does this equal U dot V plus U dot W? What do you think? Do you think it does that? These are dots. Do you think it does that? We cannot just assume it does. All right, well, if you don't know, let's try and see if we can determine it. All right, let's see if we can figure this out. Let's start with this left-hand side over here. Do you agree that this is the same as U1, U2, dotted with V1, V2 plus W1, W2? Isn't that me rewriting this left side using component form? Okay, let's do order of operations. Let's do what's in parentheses first. How do you add these two together? How do you add two vectors together? We talked about that a little while ago. Yep. So this is going to be a new vector, V1 plus W1, V2 plus W2. So that's the new vector I get when I add those two together, right? I don't need the parentheses anymore because I have two vectors have become one. Now dot those vectors together. So how do you dot these together? This times this, right? That's going to look like this. U1 times V1 plus W1, and then plus this times this, which is going to be U2 times V2 plus W2. With me? Now distribute these. Now I can distribute these because this is multiplication. These are just numbers. I'm just going to multiply it through. So this is U1 V1 plus U1 W1 plus U2 V2 plus U2 W2. I know this is starting to look like a bunch of craziness up here, but y'all with me on that? The question is, does that equal this, right? Does that equal this? So let me do this now. Let's look at the right side. What is this? That's U1, U2, dotted with V, V1, V2, plus U, U1, U2, dotted with W, which is W1, W2. What I'm going to do is I'm going to work this side out and see if it's equal to this. So what do we get here? This dot product right here is U1, V1 plus U2, V2. Then we have plus U1, W1 plus U2 W2. Are those the same? U1 V1, U1 V1. U1 W1, U1 W1. U2 V2, U2 V2, U2 W2, U2 W. They're the same thing. Check. It's distributive. All we're doing right now is establishing properties of the dot product. Things you can and cannot do with them. This we can do. All right, now, I told you I would tell you what the dot product means, right? Like why it's useful in terms of like what that number is, right? So it's time for the big daddy formula for this section. Now I'm not going to prove this formula. I'm sorry. It can be done. I'm not going to prove it though, and not in class. But here it is. Do they call it anything? They don't even call it anything. It should have its own name. I'm just going to call it the Big Daddy formula. Feel free to interchange daddy with mommy or mama or whatever you want. You can. Big doggy. All right, so here we go. Here's what it is. If you have a vector, u, and you dot it with a vector v, we know how to do it. If we have the components, we can multiply and get an answer. It's a number. But it's also this. The magnitude of u, number or vector? What's magnitude of u? Number or vector? Number. Magnitude of v, number or vector? Number. So it's this number times this number. So it's the product of their lengths, right? Yes? The dot product is equal to the product of their lengths. One more thing. Times cosine of theta. I had to have a trig function in there, right? Shit. Okay, so here's the idea. I need to visually give this to you. Let's say you have a vector here, u. Let's say you have some other vector over here, v. There is a natural angle formed between these two vectors, isn't there? There's a natural angle. Here it is. Theta. This is not a triangle. We're not drawing triangles. We're not doing any triangle work right now. If you take the dot product of two vectors, you get a number. That number is the length of this vector times the length of this vector times cosine of the angle between them. Okay? You all understand that? And even at this point, you may say, so what? Right? So what? You can take a dot product and you can get some number in who, like, what is the value of that? What is the value of that? I'm going to convince you, but I need to first establish some things here. So we're done with that formula. Okay, let's take a look at an example here. I'm going to give you two vectors. Here's one. Call that u. I'm going to give you another vector over here. V. These are just floating around on a sheet of paper. Where's the angle between them, theta, that I'm talking about in this formula? What would theta be for this picture? What would you have to do? What's that?
It'd be on the top side of the u vector.
Top side of the u?
Add the tails together.
Yeah, put the tails together, okay? Now, am I allowed to do that? Yes, I can move vectors around, right? You just can't change their direction or their length. So what I would do is I would take this vector right here, I just kind of slide them over like this, and then I bring them down like that, and then I draw that vector like that. And that would be u, right? And there is a natural angle between these two. But one could argue that there's actually two angles between them. There's this one, and there's this one, right? So which one is it? When we talk about theta in this formula, are we talking about the angle this way or the angle this way? We're always talking about the smaller of the two. All right? We're always talking about the smaller of the two. So this is your angle, theta. So what we do is we put a restriction on that theta. We say that that theta must, well, what must it be between? So between what? Yeah, so think of the different scenarios you could have here. If I have two vectors, right? That would be an angle that's smaller than 90 degrees. What if they were both like this, pointed in the same direction, like that? What would the angle between them be? 0, okay. And then we could go all the way up here, come around. My angle is still smaller than pi. And then once I got to pi, 180 degrees, then if I went over like this, now we're talking about this angle, which is still smaller than 180. So does that make sense? Like this angle is bigger, but now we're always talking about the smaller of the two. So now this one becomes my angle. So this theta that we have in this formula should always be between 0 and pi. If you like, 0 and 180 degrees. Okay, so that with this formula, it's the smaller of the angle between them. Yes? Okay. All right, I needed to establish that first. All right, you ready to see this in action? You ready to see this in action? Like what the value of something like this is? Yeah, that formula is there. Here we go. Example. Please draw a quick little two-dimensional plane here. I'm going to pick some arbitrary points out here. 1, 2, 3, 4, 5. I'm going to go 5 units each way. I'm going to go to this point right here. Just so we're clear, that's the point 2, 1. I'm going to go to the point here. This is the point 3, 4. And then I'm going to go to the point four, 2. See those points? Those points are the vertices of a triangle. In other words, those are the corners of a triangle. So now I'm going to connect them with 3 straight line segments. See our triangle? My question to you is whether or not that's a right triangle. Now, it might be obvious just by looking. I don't think it is, but how is this related to this? Right? Like, how is this connected? So here's what we're going to do. We're going to kind of take our triangle pre-cal trigonometry goggles off, and we're going to put our vector goggles on, and we're going to look at this from a different perspective. we're going to see an angle. Let's talk about this one right here, theta. Now there are 3 angles in this triangle, right? But let's just focus on that one, theta. Do you see that we could be talking about the angle between a vector that goes from here to here and a vector that goes from here to here? Yes? Do you see the 2 vectors and you see the angle between them? All right, let's call this vector here, let's call that u. And let's call this vector right here v. Can you tell me what the components of u are? And this goes back to last class, which was before our test. How do you find a vector connecting 2 points? And I said it was important where you start and where you end. Do you all remember how to do this? How do you get the vector u? You do what? You what? Tip to tail. Yes and no. I'm not quite sure what you mean by that. We have the points, don't we? How do we come up with the components from those points? We're trying to go from here to here. You take the x-coordinate of this point and subtract the x-coordinate of this point. So this should be 3 minus 2, comma, now to get the y, bless you, you do 4 minus 1. Do you remember doing that? Okay, and then this is now the vector, the displacement vector between those 2 points, which is the vector 1, 3. Good? Okay, how about the vector v? What's the vector v? So 4 minus 2, 2 minus 1, which is the vector 2, 1. Yes? Now, let's come over to this formula. Could you right now calculate u dot v? Could you dot these 2 vectors together for me? Yes? Right? So I'm about to, watch me plug everything into this formula right here, but I'll do it right here. So if I take this formula, u would be the vector 1, 3, and I'm going to dot that with the vector 2, 1. That must be equal to, according to this Big Daddy formula, the magnitude of u. What is the magnitude of u? So do you know how to find the length of this vector? Square root of each of these pieces squared. So this would be square root of 1 squared plus 3 squared. That's the length of u. What's the length of v? Square root of 2 squared plus 1 squared. And then times what? Cosine of theta, right? Aren't we trying to figure out what theta is? I'm trying to figure out what this angle is. And look at what I've done. I've filled out this equation. The only thing I don't know is what's cosine theta. So I'll be able to use an arc cosine at some point to figure that out. So let's actually compute this. What is this dot product? 1 times 2 is 2, plus 3 times 1, so isn't that 5? Left side is 5. Equals root 10 times root 5 cosine theta. Are y'all all right? You following the computations here? How do I get what?
Sorry, for 5 equals, how do you get 5 again?
Dot product here. So when you do the dot product, you're doing 1 times 2 plus 3 times 1. Right, that's what we just talked about, dot product. Not this formula, the first formula I gave us for dot product. All right, now I'm going to do this. 5 over root 50 equals cosine theta. So I just said root 10 times root 5 is root 50. And I divided it on both sides. And now I'm going to break my calculator out. And I'm going to do arc cosine. All right, I'm going to take arc cosine both sides. So arc cosine of 5 over root 50 should be equal to theta. I have some good news that our calculator is only going to give us an answer between 0 and pi, because arc cosine is only defined between 0 and pi. And therefore, well, that's okay, because this is only considering angles between 0 and pi. So we're all good here. What does the angle come out to be?
45.
45. Does this mean it's a right triangle? Nope, not yet. So what would I need to do now? I know you don't have an appreciation for this right now. I can understand the difficulty, but let me just ask you to think about something before you throw this idea, before you just like cringe at this. Let's say that I have a point. See that fire extinguisher thing right there? Point there. Let's say we have the tip of this bottle is another point, okay? And then you see the projector? Let's just say the projector is another point. So you have 3 points in 3-dimensional space. Creates a triangle. Is that a right triangle? That is very difficult to do without vectors. So like this problem right here, we could have probably have already done this problem had we not used vectors. Because you could just do some like law of sines, and you could do some different formulas and we could do it. But once you move into 3-dimensional space, it becomes very difficult to do any sort of easy stuff because you're not flattened on a sheet of paper. So to do that problem, what I would do is create a vector from here to here, vector from there to there, angle between them I could get with this formula. And it would take me two, I need to do this twice. I need to find this angle and then one more of these, because they have to add up to be 180, right? So as soon as I find the next one, if the next one turns out to be 45, I'm in business, right? I have a right triangle. Yes? Okay. Now I still haven't shown you the absolute beauty and power of the dot product, but we're on our way. So let's find another angle. So far we have not answered the question. All right, how about this? Let's call this angle up here, how about alpha? I feel like we haven't used alpha much. So according to the Big Daddy formula here, I can do this again, right? But this time my formula is going to have alpha in it. And I need, unfortunately, 2 new vectors. I need the vector going from here down and the vector going from here down. And I don't want to call them, well, do you want to call them U and V again? Is that okay with you or not? You want to use W and some other? You want to use different letters? Okay, so let's call this one W. And let's call this one B, no, Y. You want to use Y? I don't care. As long as you put the vector on it, I don't care. So back here on the formula, we can't use U and V anymore, right? Because we changed it. So it's going to be WY. WY is cosine of alpha. You should be able to tell me what W is pretty cleanly. Because isn't W just pointing the same length, but just pointing in the opposite direction of this one? Isn't it? So how do we point things in the opposite direction? Multiply it, scale it by -1. So isn't just this vector with both negatives in it? Okay, so this vector W is the vector -3. Now what about the vector Y? This one we haven't gotten. So how would I get Y? 4 minus 3, good, minus, or comma, and then 2 minus 4. So since we're going from here to here, we start with the 4, take away 3, then 2, take away 4. So it is the vector 1, negative 2. So 1, negative 2 here. This must be equal to the magnitude of W, which is the magnitude of this guy. What is the magnitude of that vector? It's the sum of each of those things squared. It's root 10 still, isn't it? Square that, square that. So you get 1, you get 9, add them 10, take the root. So this is going to be root 10. What's the magnitude of y? So here's y. What's its magnitude? 1 squared plus 2 squared, which is 5. So root 5, it's root 50 again, isn't it? And then cosine alpha. Good? We can solve this for alpha now after a little bit of work. So what is this dot product here? I forgot to put the dot in there. Dot, dot. So what's this dot product? Negative 1, right? Negative 1 plus 6. That's going to give us 5, isn't it?
Oh, no, sorry.
Right? We did this. That's negative 1 plus these two multiplied is 6. So root 50 over here again. Is this the same computation we just did a second ago or no? Wasn't it? 5 over root 50? There we go. So alpha is 45. Which means it is a right triangle. I did not mean for it to be a right triangle. I randomly made up this problem. Had a feeling it might be, but so how do I know it's a right triangle? 45, 45, there's only one more angle left, right? They have to add up to be 180. So far 90s, so only 90s left. All right, we have about 15 minutes, and now I can give you what I think is the most important property of the dot product, all right? This is all cute, and it's a nice way to find, work with triangles, especially in three-dimensional space. Especially in three-dimensional space. While I've got you here thinking about this, let's say we have two vectors like that, okay? I've already told you that the dot product gives you, like, the dot product of these two vectors is this length times cosine of the angle between them, right? Yes? I wonder what the cross product gives you of those two vectors. Well, the cross product gives you a new vector, right? Gives you a new vector. I already told you it does. But it turns out that if you take the length of that vector, the length of the cross product, and take half of it, I know this seems crazy, that will actually give you the area of that triangle. So you see this vector creates a triangle.